Welcome to the lesson video on bagging. In this video, we're going to start with a little historical story. So we're going to be talking about ensemble predictors. And so an ensemble predictor is a predictor where you make a bunch of individual predictors and you combine them to get a higher accuracy predictor. And so we're going to tell a little bit of history about what's probably the first ensemble predictor. And it's also the history of Bayes' theorem. So it's worth something that's worth knowing about. And so we're going to start talking about Reverend Thomas Bayes back in the 1740s. He wasn't really a statistician or a professional mathematician or scientist. And he was playing with some ideas. And so the idea that he wanted to work with, that he was trying to understand, is the following little puzzle. I have a table behind me. I've placed a ball on that table. And I want to figure out where that ball is on the table, left to right, front to back. And so what Thomas Bayes did is he took another ball, and he had an assistant that would stand behind him, and he would throw his ball over his head. And his assistant would look at where it landed him and say, the ball on the table is to the left of where yours landed, or to the right, and to the front or back. And then he would do this again, and throw the ball again. And repeated throws would give him the ability to infer where the ball that was behind it was originally located. So if 70% of the time his assistant said, your ball is to the right, then he knew the ball on the desk was 70% of the way to the left. Assuming, this is a big assumption, that his throws of his ball were all different, were perhaps a uniform distribution over the table of where they would land, or some at least known distribution of his throws. So assuming he could get variety in his throws, right? If he threw the same ball over his shoulder exactly the same time, his assistant behind him would give him the same answer every time he threw it. So he has to get variety in his throws, and that would allow him to infer where the ball is. And so this might be considered the first ensemble predictor where he did these individual events and then tested them against some data point and then combined the results. It's only loosely an ensemble predictor in that sense, but it's a really nice story about where Bayes' theorem, and he invented his ideas, what we call Bayes' theorem, trying to work out that little puzzle with tossing a ball. His work, he didn't publish it. It was published eventually by a friend of his, Richard Price, after he died. And then Laplace, French great mathematician and physicist, studied motion of planets, had rediscovered Bayes' theorem later on and gave the first formal description, which we have on the screen here, saying the probability of a cause given an event is proportional to the probability of the event given its cause, and he wrote the Bayes' theorem in the modern notation that we're familiar with. Laplace, in addition to fleshing out the Bayes' theorem theory and using it to calculate astronomical values, he also invented or developed the central limit theorem and many other things. Okay, so on to the subject of our video, which is bagging. And bagging is a process for building an ensemble of trees or an ensemble of predictive learners. And so bagging is actually a combination of two steps. The bootstrap step, which is something we've talked about before, taking repeated random samples of data, and then doing aggregating on the bootstraps, or bootstrap aggregating, which we combine to get the word bagging. And bagging is training a predictor on each bootstrap sample to create a new predictor that averages the results. So why? The individual predictors in this process will be different. Remember, Bayes had to throw the ball differently every time. All these predictors will be different because they're trained on different random samples of the data, making the average of those predictors robust against overtraining, which increases accuracy. Also, bagging creates an ensemble which enables the computation of out-of-bag error rate, which can act like cross-validation. And so we'll see that that's a benefit of bagging as well. Okay, so the bootstrap process. We have our original data here, and then we just take random samples of that data. And these are random samples with replacement. So meaning we take our original data, we pull out a data point, and then we pull the next data point in our sample. It might be one of the data points that we've chosen previously. And so we make these random samples of our data. Then we look at each random sample and we train a predictor on each bootstrap sample. So we train, this tree's been trained on this random sample and it's gotten the prediction regions we see here. And then here's a different tree, presumably more complex in this picture, that's been trained on this random sample and has these decision surfaces. And so on for all the rest of our trees. Now, one of the things that we're going to be dealing with are called the out-of-bag samples. So if you notice right here, there's a sample, but when we took our random sample, that observation or that data point wasn't included. So it's a data point in the original data that's not included in this bagging sample, and those data points that are not included in the bagging sample are called the out-of-bag samples. So that's a term that we're going to use in a moment. So then we take all of our different predictors. In this case, we're looking at trees because trees are really common for bagging. We take all of our different trees and we combine them to make one ensemble predictor. And this ensemble is created by averaging over the predictions of the individual predictors. So if we're doing a classification problem, suppose a new data point comes in and we want to know what should that data point there right be. Well, we would apply all of the trees in our ensemble to that data point and we'd see, oh, all of them define that as green, so that should be green. If we're right here, we would approximately, I'm not quite sure where that is on each graph, let's say here, here, and here, or maybe it's there. Anyway, we would say if 2/3 of them say blue and 1/3 says green, we would label that point as green. And so we just take a majority vote is the way we do it. If we're computing the probability that that's a certain class, it would be the fraction of individual predictors that assign to that class. So that would be the probability for classification. Now, if we're looking at regression, we look at the average output. So if you have your data point, you look at the prediction of each of the individual predictors on that data point, and then you just average over the output from those individual regression values. So again, we mentioned this terminology. Here we have the out-of-bag samples. And then what we can do is we can take the out-of-bag samples for one of our trees, and we can apply every other tree to those out-of-bag samples because those other trees haven't been trained on those samples. And we can get the compute the error rate for those other trees on those samples. And that's called the out-of-bag error. And we do that for all out-of-bag samples in all of our trees. When you have a lot of trees, the out-of-bag error approaches leave one out cross-validation. So the out-of-bag error is a really nice validation method that gets computed while you're building your trees, and then you get an out-of-bag error rate while your random forest is created. So this process of creating a bunch of individual predictors and then combining them to make your main predictor, it's called an ensemble. That predictor that's made from all the individuals is called an ensemble. And the example we're looking at here is an ensemble of trees created through bagging. So review what we've talked about. After our little historical story, we've talked about the bootstrap, which is a process of taking retreated random samples of data. Then we talked about bootstrap aggregating, or this process of bagging, where we train a predictor on each bootstrap sample and then create a new predictor that is the average of the results on the individual predictors, and that creates an ensemble. Why do we want to do this? The individual predictors are going to be different, making the average of them robust against overtraining and increasing accuracy. This process of bagging enables computation of the out-of-bag error rate, so we get a nice measure that acts like cross-validation. And the new predictor is called an ensemble. Thank you for watching.